So the physical system I want you to think about is electron. Now you might think we've already been talking about electron. We have not been talking about this particular aspect of electron. So just so that these different contexts are clear, what you have seen, where you have seen the quantum mechanical aspect of electron is in electron in a hydrogen atom. So you have proton here. We can say, all right, it's heavy enough. It's not moving. It's a passive actor. It's not doing anything. And with the description of electron, we started out with somewhat classical description. Maybe it's going in an orbit around it. And then later, with the whole stability of a hydrogen atom and whatnot, we developed it more, and we introduced the de Broglie hypothesis that this behaves like a wave. And one way to explain the stability of a hydrogen atom is that so as it's orbiting, the wavelength of the electron has to be such that if it's that it's a circular standing wave. Like that sounds familiar from when we covered the Bohr model, right? So let me just draw a version of it. So something that looks like this maybe, and if you draw it correctly, then it completes so that it's a circular standing wave. So that's the hypothesis that Bohr made, that angular momentum comes in quantized quantities of h bar. So angular momentum is n times h bar. That's Bohr's hypothesis. As we covered last time, it's not completely correct, but it's starting from correct intuition. And an aspect of this does carry over to the correct, fully quantum mechanical treatment. So I don't want to entirely step away from that. So that's the electron angular momentum we have been talking about so far. And it's different from the kind of angular momentum we are going to talk about now. To draw that distinction in quantum mechanics, we call them by two different names. We call this kind of angular momentum, well, the same thing we've been calling orbital angular momentum. Because it's angular momentum having to do with orbit. And the kind of angular momentum we are going to, that's described by the matrix mechanics that we will work with today, is we call that spin angular momentum. And I think the best way to highlight the newness of this idea is to first highlight how spin angular momentum is not a new thing in classical mechanics. So, I mean, you could have talked about spin angular momentum and orbital angular momentum, as in, I don't know what to orbital, let me use this. So if I have this, and I have this little ball, for angular momentum of this ball, I could have talked about its orbital angular momentum as it's going around in orbit. Or I could have talked about its spin angular momentum as it's spinning about its own axis, right? That's where the language is borrowed from. But in classical mechanics, there's no fundamental difference between orbital and spin angular momentum. In classical mechanics, they are both described by the same general relationship, because in classical mechanics, they are both described by angular momentum is equal to r cross p, right? With the orbital angular momentum, what we call orbital angular momentum in classical mechanics, what you're doing is, all right, this thing, it's small enough compared to its lever arm. I can say it's more or less a point mass. So it's point mass orbiting at this, so it's just mvr. Now, if it's a spin, then you have to imagine taking this, breaking a little tiny, oh, this is bigger. You have to imagine taking this, breaking a little tiny little pieces, but each portion of the mass element, you still do apply this. And you integrate it over the entire body, you get the spin angular momentum that way. So in classical mechanics, they are both described by the same basic description. That's what I mean by spin angular momentum is not a new thing in classical mechanics, just a different name for a particular arrangement. And so in quantum mechanics, orbital angular momentum, it's not all that new. That's why we could describe it sort of semi-classically. And in fact, when you do a rigorous treatment of orbital angular momentum, the way people do it is, well, you take the classical relationships and you simply turn this into operators. It becomes very much more complicated mathematical thing because now you're dealing with the derivatives and gradients and whatnot. I can actually describe it to three-dimensional. I've given up doing that without prior preparation. Anyways, so it becomes mathematically complicated, but the roadmap is there. It's not something new. That's why I want to tell you that spin angular momentum is a completely new concept in quantum mechanics. Now, to kind of oversimplify it, you might say spin angular momentum is, well, think of electron like a ball. Here's my electron. Think of it like a ball, and it could be spinning, like the way we talk about it in classical mechanics. And if it's spinning like, if it's spinning in this direction, something like that, look at it from top, counterclockwise, then you would say, then it's a spin angular momentum points up. This is the direction of its spin angular momentum. You could say that, and this is sort of like it's a fairy tale. There is a kernel of truth in there, like with many fairy tales, be nice to other people or whatever. But much of it is made up for pedagogical purposes. For one, describing electron like a sphere, that's a completely unphysical description of electron. Electron, as far as we know, is a point particle. It has no size. We have not discovered the structure to electron. We don't know the size of electron. So it's a pointless thing. Like if it's at a single point, how can it be spinning? Like a point doesn't spin. The second thing is this. So if a quantum mechanical spin could somehow be reduced down to orbital angular momentum of some kind, the way it works out in classical mechanics, spin angular momentum would obey a similar rule as what the orbital angular momentum does. And the very first thing you see is that it doesn't, because we are going to be talking about the spin half system. With electron spin, this is the first thing you need to know about its property. We talked about the quantum numbers on Tuesday, right? There's the principal quantum number, orbital angular momentum quantum number, and the magnetic quantum number. So looking at orbital angular quantum number and magnetic quantum number, orbital angular quantum number went 0, 1, 2, and so on. And there was maximum kept by n-1. And the magnetic quantum number, it went from minus L plus 1, and so on, all the way to plus L, right? So there are similar set of quantum numbers you can assign to electron that's associated with spin angular momentum. And this is what I'll tell you. Spin angular momentum quantum number is just 1/2. That's for the electron. If you have a different particle, they may have different spin angular momentum magnitude. So if we want to stick with this fairy tale analogy of how electron spin is like this particle, this thing, spinning around some axis, we could say, well, this whole spinning thing, it never slows down. Because no matter what you do to it, it'll always have this spin angular momentum magnitude. It'll never go down to 0. It'll never go up to any other value. The only thing that could change with the electron is what direction that spin points in. And that direction is described by similar magnetic quantum number, m sub s, so that we don't confuse that with this m. And it actually follows the same rule as this does. It starts from minus s, so I guess minus 1/2. minus 1/2. And it increases by 1 until it reaches plus s. So minus 1/2 plus 1 is what?
1/2.
Plus 1/2. Okay. Oh, I'm already there. So I guess I'm done. So you have two values. So because there's only two values, sometimes we call this a spin up and spin down. So let me point out what makes this so incompatible with the description that we are using for orbital angular momentum. So this description here, it's based on this mental image of something completing a standing wave, right? Look at this thing that has a half integer spin. It doesn't travel in a standing wave. Unless you somehow, for the spin, you give it, when it comes around the once, you decide, that's not enough, go around the one more time. Then it's, why only twice? Why not 3 times? So what it is this is a completely new quantity. Spin, quantum mechanical spin has no classical analog. It's a purely quantum mechanical idea. That's really the best place to start. And you can ground it in one thing, that it is still angular momentum. So depending on the kind of interactions you have, you can have an interaction that conserves the total angular momentum, but where spin angular momentum transfers to the orbital angular momentum by changing this by 1. So it is still angular momentum, but how it's described, there's no analogy in classical mechanics.